All right, let's take a look at pH versus solubility. So the solubility of a slightly soluble salt containing basic anions increases as H plus increases. So what I mean by that with the basic anions is something like magnesium hydroxide down here. So magnesium hydroxide, that's a solid. It's not very soluble in water. When it does dissociate, it produces Mg2 plus and a few OH minuses. So the amount of reactants, the amount of the anions and cation that's going to produce is going to be fairly low. But those that it does produce, this hydroxide right there, that hydroxide is what's going to make this solution slightly basic. So that's what it means by salts, soluble salts containing basic anions. There's your basic anion. So if you increase the H plus concentration, that's going to increase the solubility of this particular guy right here. So the reason for that is if we look down here when we add a strong acid, so a strong acid, remember, is something that completely dissociates, and when it does completely dissociate, it produces those H plus ions. So we can see down here that those H plus ions that we add, they're going to react with those hydroxides. Okay, so this 2H plus is going to react with those hydroxides. So let's move that arrow. So those hydroxides right there that we're talking about, that's those hydroxides right there. So when we add the strong acid, it reacts with those hydroxides to produce water. So essentially what we're doing when we add those H pluses is we are eliminating some of this hydroxide. And what happens when we eliminate something from one side of the equilibrium? We stress the system. And when we stress the system, the equilibrium is going to shift to try and fill in that hole. So when we take away some of those hydroxides, equilibrium will shift towards the reactants to fill in that hole. So what that means then in essence is the concentration of the magnesiums is going to increase as we add that H plus. So we're changing the pH because we are getting rid of hydroxides and we're adding in the H pluses. As that happens, as we add those in, the solubility of this particular salt is going to increase. So the second reaction reduces the hydroxide in solution and drives the first equilibrium to the right. So as this reaction happens and it goes to completion, okay, the H pluses are neutralizing the OH minuses. It's going to drive the reaction towards the right. So here's what the net ionic equation would look like. The H pluses react with the OH minuses to produce water, leaving the magnesiums and their concentration increasing. So here's an example then. Let's say we add solid calcium carbonate and it's placed in a solution of hydrochloric acid. So of course you guys have all your solubility rules memorized, so you know that calcium carbonate is classified as insoluble. It's CaCO3. But as we talked about before, insolubility doesn't mean that it's actually insoluble. All ionic compounds are soluble to some degree. But in the case of calcium carbonate, its solubility is so low that we just go ahead and consider it insoluble. Those that do dissociate into Ca2 plus and CO3 2 minus. But the amount of reactants is going to be so low that it's negligible, and so therefore we consider this compound to be insoluble. However, if we drop it into a solution of hydrochloric acid, so that means we're adding H pluses. Okay, the Cl minuses, they're not strong enough to actually do anything, so they're just going to stay Cl minuses. They will react with, okay, so let's see, who would they react with? Would they react with the calciums? No, because the calcium is plus and H plus is going to react with a plus. Would they react with the carbonates? Yeah, there's a 2 minus right there. I bet you that'll work. So CO3 2 minus, and when those react, they're going to combine to form carbonic acid, a weak acid, and since carbonic acid is H2CO3, that means we'd have to add 2 H pluses. So we're going to double the concentration of hydrochloric acid to match up with the calcium carbonate. So those H pluses are reacting with these CO3 minuses, so this is just the CO3 right here that's being produced. It's reacting with the H pluses. And when that happens, we can go ahead and cancel those out. And our net ionic equation would be CaCO3 plus 2H plus turns into calcium 2 plus and H2, let's see, H2CO3. But remember, H2CO3, when it is created, it decomposes into H2O. and CO2. Just something you just got to remember, and that's what it decomposes into. So this right here would be the correctly written net ionic equation if this was a question on the AP test, question number 4. This is what you would want to record. So what happens then is, notice how we're creating these Ca2 pluses, even though this is normally an insoluble compound, by putting it in a pH solution or an acidic solution with a higher concentration of H pluses. We drive this equilibrium over to the right, thus producing more of the Ca2 pluses. So we're increasing the solubility of this guy right here. So we can actually, if this was in the solution, we could get it to where this would all dissolve or all ionize. Okay. Doesn't mean we're going to have the carbonates in the solution, because the carbonates are getting reacted and turned into something else. But we're increasing the solubility of this because this is being forced to ionize. Okay, now solid magnesium oxide is added to a solution of nitric acid. I'd recommend go ahead and pause the video right here, give this one a shot, write out the net ionic equation, and then resume it to check your answer. Good to have you back. So let's take a look at this problem. Magnesium oxide, MgO. We should remember that oxides are not very soluble, if soluble at all. And so this is going to ionize, when it does, into Mg2 plus O2 minus. And if we add the H plus to this system, because it's in nitric acid, which is HNO3, the nitrates, they're going to stay soluble, so why even write them in there? And who is that going to react with? Yeah, it'll react with the anion, so the O2 minus. And when this happens, what do you think that's going to make? It's going to make water, H2O, and we're going to need 2 H pluses for that to happen. O2 minus created and destroyed, so we can get rid of that. That means the net ionic equation will be magnesium oxide plus 2 H pluses, yielding Mg2 plus and water. And we could do something fairly similar with weak acids. So the solubility of slightly soluble salts containing basic anions increases, H plus increases. That's what we just talked about. So when you add those hydroxides, or when you've got a salt that makes those hydroxides or makes basic anions, H pluses are going to neutralize those and drive the equilibrium, increasing solubility. So the only thing really different between this one and with the strong acids is that now we have 2 equilibriums being set up. So before, when we added a strong acid, that means it was H plus and only H plus reacting with the hydroxides. Now, since it's a weak acid, that means the acid itself doesn't completely ionize, and so this reaction doesn't go all the way to equilibrium, or all the way to the right. It goes into equilibrium. And so we wind up with here this going on. If we take a look at just what's happening, so these 2 hydroxides that are being produced by the magnesium oxide, well, they will be neutralized by this acetic acid right here. So that's going to eat up those 2 and then generate the H2O and the acetate ions. So these are created and then destroyed. When you destroy those, take it out, you're stressing the system. When you stress the system, it's going to shift to fill in that void. So MgOH will then solubilize or ionize some more to refill in that void. So then the net ionic equation would be the magnesium hydroxide plus the 2 acetic acids, generating Mg2 plus, water, and acetate. Hydroxides aren't in there because they're created and then destroyed. All right, let's look at an example. So solid calcium carbonate is placed in vinegar. So vinegar, hopefully you guys recognize by now, is acetic acid. So anytime you see vinegar, that's acetic acid. You should know what the acetate ion looks like, and you should know that acetic acid would just be the acetate with an H. So solid calcium carbonate, and calcium carbonate we've already said is not very soluble. But when it does, the little bit that does ionize would be Ca2 plus and CO3 2 minus. When we add this to CH3, COOH, there's our acetic acid. That's going to react with our anion, so our CO3 2-. And notice how this one does not produce the OH minuses in the solution, so it's not necessarily always hydroxides. It produces the carbonate, which would be a basic anion. Because of the way it interacts with water, it's from a weak acid. And so that's going to, it'll set up equilibrium, and that's going to make H2CO3. You should be telling yourself right now what the H2CO3 is going to change into. CH3CO2-, just going to shorten that, same thing. And just to balance this out, we would need 2 vinegars for every 2 acetates. Alright, so carbonate is created, then eaten up by the acetic acid. Yum, 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 yum. And CaCO3 is going to react with 2CH3CO2H. And that's going to be at equilibrium now with Ca2+. Plus, alright, so you guys already told yourself, what does carbonic acid decompose into? That's right, water and CO2. And along with those, it's also going to be producing the 2CH3CO2-, the acetates. So there you go. Difference is here that we have that undissociated acid in there, so it's not just the H pluses that we're dealing with, and that winds up being on both sides. It's like HCl, its anion would disappear. We wouldn't deal with the chloride at all, but with acetic acid, a weak acid, we put that acetate on both sides of the solution, both sides of the reaction.